34 billion individual transistors, meticulously orchestrated on a 4-nanometer die, an engineering miracle that was severed from its future by its own creator. This is the AMD Z1 Extreme inside the ROG Ally. It condensed the processing power of a massive desktop gaming tower into a portable frame weighing merely 600 grams. In 2026, just 30 months after its launch, Advanced Micro Devices halted dedicated driver development for this chip. The architecture was effectively abandoned. This postmortem analyzes the systemic reality of how the technology industry discards its highest engineering achievements. To understand the weight of this decision, we must first conduct an autopsy of the silicon and confront the physical impossibility of its existence. For decades, x86 computing was governed by a strict physical law. Massive processing power required massive power draw and massive cooling solutions.
High-end performance was physically tethered to copper heatsinks and a continuous high-wattage feed from a wall outlet. The handheld APU era shattered that tether. It forced a desktop-class graphics pipeline to operate within a 15-watt envelope, without relying on the luxury of giant fans or unlimited electricity. The Z series represents a violent rebellion against the established boundaries of thermodynamics. The lineage of this defiance began with the custom Van Gogh APU inside the Valve Steam Deck. Engineers faced a brutal baseline constraint. The entire system had to survive on a strict 16-watt thermal budget. To maintain that limit, AMD strangled CPU memory access. Total bandwidth offers 88 gigabytes per second, but the CPU is artificially capped at 25. The remaining 70 gigabytes funneled to the GPU. Furthermore, sluggish clock ramping policies prevent sudden peak frequencies to protect battery voltage. In the handheld era, engineering performance is defined by the relentless, intelligent deprivation of resources. As the Z1 and Z2 Extreme evolved, the struggle moved from total wattage to spatial density inside high-tech foundries. AMD introduced compact Zen 4C and 5C cores, which are often dismissed as inferior microarchitectures intended only for light workloads. This proves the compact core uses the exact same microarchitecture logic as the high-performance core, just physically compressed to save 35% of its footprint. By utilizing a dense six-transistor SRAM architecture, engineers shaved transistors off memory cells to shrink the physical silicon. Reclaiming those microscopic millimeters was the only way to fit a desktop pipeline into a handheld without melting the chassis. The tension reaches its peak in the Z2 Extreme, which attempts to run 16 compute units on a single 4-nanometer die. At this scale, the primary challenge is no longer computing cycles, but heat evacuation and power delivery management. Engineers handicapped peak gigahertz to maintain a flat power curve, locking the 28-watt threshold. The brilliance of this design lies in its ability to balance on the razor's edge of catastrophic thermal failure. We return from the microscopic die to the macro reality of 2026, the total abandonment of the Z1 Extreme. This pivot was forced by corporate warfare, as Intel's Panther Lake architecture arrived to challenge AMD's handheld monopoly. Millions of hours of human ingenuity went into solving the specific thermodynamic constraints of the Z1 die, yet it was given a commercial lifespan of only 30 months. This is the era of planned obsolescence, where even history-defining custom silicon is treated as disposable. Modern handheld PCs are fragile thermodynamic machines caught in an unsustainable iteration cycle. Microarchitecture represents the most complex physical structure ever designed and mass-manufactured by human beings. Yet we have engineered an economy where our most miraculous achievements are ruthlessly destined to become e-waste.